purpose of this video is to show you that kinetic energy equals work. When we did the matchstick rocket lab, you saw that kinetic energy is defined as the energy of an object that's due to the object's motion. We can also define kinetic energy as the ability of an object to do work. And what we're going to do here is we're going to prove that this is true. I should let you know, and you'll see this later on in the video as well, that the equation for kinetic energy is 1/2 times the mass of an object times the velocity squared. That's important when you see where this comes from in the next step. We get that expression for kinetic energy by using the fifth uniform equation of motion, which is Vf squared equals Vi squared plus 2a, and we're going to call this d today. I'm going to rearrange this equation to isolate the acceleration and the distance. All I did there was subtracted Vi squared from both sides and divided by 2. Now I'm going to recall Newton's second law of motion, that force equals mass times acceleration, and therefore force divided by mass is the acceleration as well. And I'm going to substitute that expression into the fifth uniform equation of motion. I'm also going to break out the 2 and call that 1/2, because dividing by 2 means the same thing as multiplying by 1/2. And this is going to equal force times distance over mass. Now what I can do is multiply both sides by the mass. And I'm going to see that I end up with 1/2 mass Vf squared minus Vi squared equals force times distance. On this side of the equation, you'll see that that's work. Force times distance is work. The cosine is not there, but that is going to be thought about in the direction that the force is going. And I'm going to take this other side of the equation, and I'm going to distribute the 1/2 times the mass to get 1/2 m Vf squared minus 1/2 m Vi squared, which looks like the initial kinetic energy minus the final kinetic, subtracted from the final kinetic energy. And I can sum this up by saying this is going to be kinetic energy final minus kinetic energy initial equals work. Or we just proved the work energy theorem, that the change in kinetic energy is the work done to a system. So change in kinetic energy in a system is the work done on the system, and we get that from the uniform equation of motion number 5 and Newton's second law. Let's see how this plays out in a work kinetic energy problem. Before we get there, these are two expressions that you should write down. Change in kinetic energy is going to be equal to 1/2 times the mass of the object times the change in velocity squared, which is also going to be equal to the total net work done in the system. If I was to take the kinetic energy at one moment in time, then I can say the kinetic energy at that moment in time, if I know that object's velocity is 1/2 times the mass times the velocity squared. Pause the video here. Make sure you have those equations written down in your notebook and define your variables, because you're going to be using those equations quite often for the rest of this unit. So here's your kinetic energy work type of question that you're going to be asked in the homework. Student is wearing frictionless roller skates on a horizontal surface pushed by a friend with a constant force of 45 newtons. How far, find distance, must the student be pushed starting from rest, VI equals 0, so that her final kinetic energy is 352 joules. KE final. Second part of the question is, if the student has a mass of 60.0 kilograms, what will be her change in velocity? So there's two parts to this question. First part is going to ask for how far the student was pushed, but we're going to use the work-kinetic energy theorem. So I know this is going to be final kinetic energy minus initial kinetic energy equals force times distance. I can divide both sides by the force to isolate the distance. And I also know that the initial kinetic energy in the system has to be 0, because kinetic energy is 1/2 mv squared. If the velocity is 0, then the whole entire thing is going to be 0. So initial kinetic energy is 0 in this case. So I know the final kinetic energy is 352. I know my force is going to be 45. And that's going to give me the distance. And when I divide that out, rounding to 2 sig figs, I get 7.8 meters. So that's how far the friend was pushed on her roller skates. Second piece here is going to be, what was her change in velocity? Well, change in kinetic energy equals kinetic energy final minus kinetic energy initial. And I know for a fact that the initial kinetic energy is 0. So the kinetic energy final is going to be 1/2 times the mass of the person times the final velocity squared. So what I can do here is I can multiply both sides by 2, divide by m, and square root, and that's going to find me the final velocity of the girl on the roller skates. So we have 2 times final kinetic energy divided by the mass, filling stuff in, 2 times 352 joules divided by 60.0 kilograms. I'm going to end up with a final velocity of 3.43, excuse me, meters per second. So this is a good example of how we use the work-kinetic energy theorem. You will now be ready to do page 166, 1 through 5, and 168, 1 through 4. Pause the video, rewind if necessary, look at those equations, make sure you have them written down, and we will look over these together on Monday.